Hello everyone. So today we are going to start boundary value problem BVP. Okay. So let's start by considering a second order differential equation y double prime plus y equals to 0. Y double prime means the double derivative, or we can say that second order derivative of y with respect to the independent variable, which is x here. Okay. So it is double derivative of y plus y equals 0. So this is our differential equation. Now you know that we can solve this differential equation and we'll get a solution. So here I'm direct giving you the solution, which is y equals to c1 cos x plus c2 sin x. Now yx, because y is dependent on x, right? So this is our solution. Now you can see that here we have two arbitrary constants, right? And if you remember, when we were dealing with the initial value problem, there we also had this type of solution, a solution having two arbitrary constants, right? So what I told you there is that to find out the values of these two arbitrary constants, we need two conditions, right? So here when we have the solution, here also we need two conditions to find out the value of these two arbitrary constants, right? But when we were dealing with the initial value problem, we had the two conditions but at the same point. Okay, now here you can see that the conditions that are given to us are at different points. Here x is equal to 0 and here x is equal to pi by 2. But in the initial value problem we had these conditions but at the same point, and here we have these conditions but at the different points, or we can say at the end points of the domain. Okay, so this, or we can say these conditions are referred to as boundary conditions. Okay, so here a definition is given that uh, a differential equation together with boundary conditions is called a boundary value problem. So here you can see that we were given a differential equation, this, and the conditions at the boundary points, okay, or we can say at different points. We were given the conditions at different points. Okay, so any differential equation given to you with the boundary conditions is known as a boundary value problem. Okay, now here you can see that a small note is given to us that says that a boundary value problem may have infinite solutions, single solution, or no solution at all. Okay, so I'll show you this by using an example. If we take this differential equation that was given above, if we use this differential equation, then we can see that the solution of this differential equation is this, and the conditions are y is 0 when x is 0 and y is 0 when x is pi by 2. Okay, so let's try finding out these arbitrary constants using these conditions, and then finally finding out the solution that will not have any arbitrary constant. So here you can see that we have the solution, okay, and we are given these conditions. So we'll use these conditions to eliminate the arbitrary constants from this solution. Okay, so the first condition is y is 0 when we put x as 0. So we'll put x 0 in this solution. Okay, so when we put x as 0, this will become y 0, and you know that y 0 is 0, so this will ultimately become 0. Okay, so 0 is equals to c1 cos 0 plus c2 sin 0. Okay, so here you can see that 0 is equals to c1 cos 0 plus c2 sin 0. I've just put the values of x and y. Now you know that cos 0 is 1. So c1 into 1 will become c1, and sin 0 is 0. So c2 multiplied with 0 will become 0. So from this you can get that c1 is 0. Okay. Now we'll put the second condition. The second condition says that when we put x as pi by 2, we'll get y as 0. Okay, so we put pi by 2. Okay, x as pi by 2, so this will become y pi by 2, and we know that y pi by 2 is 0, so this will ultimately become 0. 0 equals c1 cos pi by 2 plus c2 sin pi by 2. Okay, so you can see here 0 equals c1 cos pi by 2 plus c2 sin pi by 2. Now you know that cos pi by 2 is 0 and sin pi by 2 is 1. So this will become 0 and this will become c2. So c2 equals 0. So from here you can also get the value of c2. So you can see that using these conditions, we are able to find out the values of these arbitrary constants. Okay, so when we put these values in our solution, we'll get yx equals c1 is 0, 0 cos x plus c2 is also 0, 0 sin x. Okay, so this whole term will become 0. So we'll get yx is equal to 0 as the solution using these conditions. Okay, so y equals to 0 is the solution of the differential equation that we were dealing with. Okay, now what if I change these conditions? If I change the conditions as y0 is 0 and y prime pi by 2 is equals to 0. Okay, that means when we put x as 0, we'll get y as 0, and when we put x equals to pi by 2 in the derivative of y, then we'll get the derivative of y as 0. Okay, so try putting these conditions now. So when we put the first condition, we know that what we'll get is c1 equals to 0 because y0 is 0. So here when we put x as 0, y0 will become 0. c1 cos 0, c2 sin 0, and you know that this term will become 0. This will become c1, so 0 equals to c1. We'll get c1 as 0. Now try putting the second condition. Here you can see that we are given that derivative of y becomes 0 when we put x as pi by 2. So first we have to find the derivative of y, right? So the derivative of yx was c1 cos x plus c2 sin x. Now if I find out the derivative of this, it will become y derivative x equals to c1 minus c1 sin x, because the derivative of cos x is minus sin x. Okay, so this will become minus c1 sin x and this term will become c2 cos x. Now what was the condition that was given to us? It was when we put x as pi by 2, the value of our derivative will become 0. So we'll put pi by 2 at the place of x. So y derivative pi by 2 equals to minus c1 sin pi by 2, c2 cos pi by 2. Okay. Now you know that the value of this is 0. So we'll put 0 here, and then you know that sin pi by 2 is 1. So 1 into minus c1 will become minus c1. The value of cos pi by 2 is 0. So c2 into 0 will become 0. So we'll get minus c1 equals 0. That means c1 is 0. So you can see that using the first condition, we got c1 equals to 0. And then when we used the second condition, the another condition, again we are getting same thing, c1 equals to 0. Then what about c2? What is the value of c2? We are not getting the value of c2 by putting both the conditions, right? That means c2 can take any value. And if c2 can take any value, okay, that means that our y will become, because y depends on this arbitrary constant, right? So if this constant can change its value and it can take infinitely many values, then y will also have infinitely many values. Okay, so that means that using these conditions, the solution will have the solution, but at the place of C2 we can take infinitely many solutions. That means we'll have infinitely many solutions when we use these boundary conditions to solve that differential equation. Okay, we'll have infinitely many solutions in this case. Now again, if I change the conditions to y0 0 and the derivative of y at pi by 2 as 1, then what? You know that putting this value will get c1 equals to 0, right? Now when we put this another condition, what we'll have is the derivative of y was minus c1 sin x plus c2 cos x, right? And we'll put x as pi by 2. Okay, so y dash pi by 2 equals minus c1 sin pi by 2 plus c2 cos pi by 2. And you know that y dash pi by 2 is given as 1. Okay, so here it will become 1 equals minus c1 sin pi by 2 is 1. So 1 into minus c1 will become minus c1, and cos pi by 2 is 0. That means this term will become 0. So from here we get that minus c1 equals to 1. That means c1 equals to minus 1. And using this, you know that from here c1 is 0. So if I put c1 as 0, what are we getting? We are getting minus 1 equal to 0. Is this possible? No. That means this case is not valid. That means we will get no solution in this case. Okay, when we use these conditions to solve our differential equation, we'll get no solution. So you can see that when I used this condition, first one, y is 0 when x is 0 and y is 0 when x is pi by 2. We got y equals to 0 as a solution. That means it was a trivial solution, right? It was a single solution. And when I changed the conditions to y0 is 0 and y derivative at pi by 2 is 0, we were getting infinite number of solutions, right? Because we were not getting the value of C2. Okay, we were not getting the particular value of C2. So we can take any value for C2. Okay, and then we'll get infinite number of solutions. We'll get infinite values of y. Okay, depending on that C2. Now in the third case, when I change the conditions to y0 as 0 and y derivative at the point x equal to pi by 2 as 1, then we had no solution because it was contradicting at the last point, that minus 1 equal to 0, which is not valid, right? So we were getting no solution at that case, in that case. So that is what the note given above meant. Okay, a boundary value problem may have infinite solution, single solution, or no solution at all. You can see in these three cases we had every type of solution. We had no solution, we had single solution, and we had infinite number of solutions, right? So that's why a boundary value problem can have infinite solution, single solution, or no solution at all. So this was all about boundary value problem. Now you should wonder that we discussed about the solutions of boundary value problem, but what about initial value problem? Okay, what type of solutions we get in the case of initial value problem? So for that we'll discuss the existence and uniqueness theorem, okay, or we can say Picard's theorem in the next lecture. So that's all for today.